This is video 4 for CS 2124. We have started looking at algorithmic backup. We have started looking at algorithmic design for our abstract data type for a linked list, and we haven't gotten very far. But the steps that we've taken, I think, are pretty solid. We've got a constructor that avoids the boundary condition of having a completely empty list. We're not going to allow that to be completely empty because it's always going to be at least pointing at the empty head node, which for the time being must look like, well, that's just an unnecessary thing that's going to be in the way. But you're going to be surprised at how easier it makes our lives once we get going on this. Speaking of going on this, we're up to operation number 3, which is insert. And that was insert something in the list. And the thing that we're going to insert is data. I'll just generically represent that as that we're given data D. Data D in a circle. That's what we want to insert. So that's going to have to go into a new node, and that new node is going to have to go into our list. And being who I am, I've got to start with a before and after picture. Before, we've got our head pointer that I'm going to write on the board so much, and it's a small board, so I'll abbreviate that with H for head. We've got a head pointer that points at a garbage head node, also known as an empty head node, and it has a 0 next pointer. So it's got a built-in sentinel to show that there's nothing else in the list. Oh, but there's about to be after. We'll still have the head pointer. We better. Class invariant. It's got to point at the empty head node before and after. Get to assume before if we're doing an insert, and we have to guarantee after. That's still going to have garbage. We're not going to put data in there. It turns out that the empty head node is just going to be handy to have as a placeholder. And there'd be some really cool questions and answers we could use to discuss that. But you know what? I'm going to save that for our chat at the end. So think deep thoughts about the empty head node and its implications. The after is just going to be one additional node over here with data D in it. And since that is now the last node in the list, that will have the 0 next pointer. Okay? So there's where we want to go. And you know what? That was so much fun. Let's do that again. Let's insert data D2 this time. And our before picture would be same as the after up there, after above. But what about its own after picture? After we insert data D2, let's discuss this virtually, mind communication throughout the ether. Is D2, does that need to replace the empty head node? No, I always start with the stupid option first. It's not going to replace the empty head node, but of course we will want to squeeze it between the empty head node and the first real node in the list. Oh no, wait. We're going to be implementing perhaps a waiting list, an unbounded waiting list for Big Blue Madness tickets. So maybe D2 needs to go at the end, after node D. In other words, we're not always going to want to put the second data value in the same place in the list every time. So the after picture, I'm going to kind of leave that hanging. I'm not even ready to draw an after picture yet because we don't know. Do we want to put it in front of the node D or after node D or wherever? Which leads us together with me leading to a recollection. Let's recall one of the advantages. The array is smiling and nodding knowingly at us right now. One of the advantages of the array was we had direct access. So all we had to do to put a new thing in the array was have the index number of the array element that we wanted to fill in. And that doesn't seem fair. Array can store a new value in any location. That's the array laughing at us right now. It has direct access. All we need is the index number of the one that we want to change. That's no fair. No fair. List doesn't have an index. But we're going to fight back. Here's our solution, or sort of a solution. Instead of having an index number that we can use. Okay, that was a special kind of interruption. I ran out of storage on the iPad. So let me see if I can pick up where I left off. I had just made the observation, I believe, that an array has an advantage over us as linked listers right now because an array has an index number that takes us right to a particular element. We don't have any such thing in a linked list. So here is kind of a workaround solution. We'll set up a current node pointer that describes itself. It points to a current node in the list, and that current node that'll be the focus. Just like if we had an index number, we would focus on a particular array element. So this is similar to index number, similar to index. How is that going to help us? Well, now we can construct a plan for our insert operation. Point cursor. Cursor is the name of this. This is not a thing that I made up. A cursor, C-U-R-S-O-R, yes, it's the same word as the blinking square on the screen. That's our current node pointer. That's going to allow us to put our finger on a particular node on the linked list and keep it there until we are able to do something like insert a new node. So I'm going to point the cursor at node in the list, wobbly whiteboard, in the list that will precede, P-R-E-C-E-D-E, precede the new node that we're about to insert with our insert operation. Why? Because the pointers only point toward, and the pictures that I'm drawing, they're always point left to right. The pointers always point forward. So if I were, for example, to make the cursor point at this node right here, then the new node I'm going to go insert in the list goes right after that one. My caffeine's wearing off. So the cursor, we're going to point the cursor, we're going to position the cursor at the node in the list that will precede the new node and insert new node. Oh my goodness gracious. Been a long day. Insert new node after cursor node. Some days I got it together, and some days I don't, and my brain just starts falling apart. It's just like regular class, isn't it? Why after the cursor node? Well, if I point the cursor here, then I can squeeze a new node in between these. If I point the cursor here at the last one, then the new node should go off the end of the list, and it'll be the new last node in the list. Does everybody have sort of the general idea? Let me draw a picture. This stuff's been on the board too long anyway. Whoops. First time that happened. A general case for our insert operation now. Be something like this. General case, not necessarily the first node, not necessarily the last node, but here's some node in the list. S for some node. T for the next node. Very generally, not the first, not the last. And what we can do is, if we've got this cursor pointer, which is a current node pointer, which is the analog of the index number in an array, if that points at S, then the way we did with our example linked list from class already, our hard-coded linked list, was if we had a new node and a temporary pointer to a new node, then what we're able to do is N for new node. Everybody has an abbreviation. What we'll be able to do is, with our temporary pointer at our end node, we could say temporary pointer arrow next and make that point to T, so that we don't have a massive memory leak of T and everything beyond it in the linked list. And then we can make cursor's next pointer point at the new node. And voila, our minor surgery does this little insertion in place without disturbing anything before or anything after that in the list. What could be simpler? Well, possibly lots of things, but before we go any further, this cursor, who's positioning that? I said we could position it at S, point it at the first node, point it at the last node, or whatever. You know what? It's got to be able to retain its value from one member function call to another, because it's going to take some separate member functions that were not in the original ADT design. We're going to have to add some additional member functions, but do nothing but move the cursor around. Move it to the front, move it to the end, move it to the middle, whatever. So here it comes, big red note, caution. So that we can hold the position, so that we can put our finger on a position in the list and keep it there between function calls, cursor will need to be a private variable. A state variable, also known as a private variable, also known as a state variable. It's part of the state of our linked list object. It's where the current node is that we're focusing on in the list. Why do we need to be careful about that? Well, it's a pointer for one thing, so we don't want it to be 0. Remember that? We don't want it to be 0. We don't want it to be a garbage value. It would be nice if it always had some meaningful value. Well, here's how we fix that. We make a promise to ourselves by way of a yet another class invariant. Just about every private variable is going to have some class invariants involving it that kind of govern it or make rules about what it can or can't be. We've got one already, class invariant. The head pointer always has to point to the empty head node at the front of the list. Here's a new class invariant. New class invariant. Cursor always points at some node in the list. And you think, well, you know what? That's exactly the way we started off with our class invariant for the head pointer, but that one didn't stay that way. We tightened that one up. We said, you know what? We need to be even more strong in that rule. We need to say that the head pointer has to point at the empty head node at the front of the list, and that's true. So is this one going to have that direction as well? Does the cursor need to always point at the empty head node? Absolutely not. Then it would completely defeat the purpose of having a cursor pointer in the first place. The cursor is free to roam back and forth anywhere in the list, anywhere we need to do something at a different position in the list than just the front or just the back or wherever. So how can we make sure this always happens? Class invariant, if I remember back to the way that it was described, all member functions get to assume it's true without testing. When we first call them, they get to get that as a given. That class invariant must be true, and they have to guarantee that it's true by the time they hit their own closing curly bracket to make sure that it's okay for the next person, the next member function that's called. How can we make sure, if we are the constructor, that's the one that's initially charged with making sure all the class invariants are true? The constructor, we've got a new mouth to feed now, we've got a new private variable. The constructor is now going to be responsible for making sure that the cursor always points at some node in the list. So what we have to do is actually go back and revise the design of our constructor. Revised constructor. Yeah, I'm falling apart here. But you're used to that. Revised constructor, before and after picture. How is it different? Well, not only do we have a head pointer now that we got to take care of, we also have a cursor pointer. And neither one of those is allowed to be garbage or 0. Otherwise, we're going to create problems for ourselves, and everybody has to test and make sure that they're okay before we're good to go. The before picture is both of these are garbage. The after picture, since they are private variables, they're not going anywhere. They'll still be here. There's still a head pointer. There's still a cursor pointer. And we know what's going to happen to the head pointer. We're going to dynamically allocate a node, a placeholder node, just to make sure the list is never completely empty. It avoids special cases that we would run into in some of the later member functions if we aren't careful. So we'll point the head at that. And now we've got this new class invariant. The cursor has to point at some node in the list. Well, you know what? There's not any other node to point at in the list. So we'll set the cursor also to point at the empty head node. Mental note, we got to go back and revise the algorithm for the constructor. Not only do we set head to a dynamically allocated new node and set its next pointer to 0, we also got to set the cursor to point at the same thing. Easy statement. I'm not even going to elevate that to having to rewrite the entire algorithm for the constructor, because all I got to do is say cursor equals head, semicolon. There it is in C++. But we do need to make sure that our cursor, our class invariant involving the cursor, is true. You know what? All of this prep and stuff and cautions and so forth, I think, am I right? I think that we are actually ready to dive in and finally work on the insert function without having to worry about all this stuff, for crying out loud. But I think I've also used up enough time for another video, so I think a lot. I'm not thinking a lot right now. I think that the next video we'll get busy with insert, because there's still going to be plenty of special cases that we're going to have to worry about in that. And I just don't know that I'm up to it right this minute. So I'll see you online.